Hi, my name is Ruhi Shah, and I'm from the University of Waterloo. My talk is called A New Model for Quantum Cellular Automata, and in my talk, I created a new model for quantum cellular automata that evolves a tensor product of qubits, and there's interesting results. Hello, everyone. Today I will be presenting to you my summer school project, which was a new model for quantum cellular automata. Okay, so the top barcode image is a recent preprint of the paper that my mentor and I published following the months of the summer school. And the bottom barcode is the function repository function that you'll need to make this presentation work if you're looking at it on Pathable. Also, a huge shout out to Jonathan Gerard. Yeah, I couldn't have done this whole thing without him, so yeah. Okay, so what is a QCA, a quantum cellular automata? So just like a classical CA where you have logical gates applied onto classical qubits, in a quantum CA you have quantum gates applied onto quantum bits or qubits. In my model, I evolved a tensor product of qubits, and I use unitary operators to evolve that tensor product. Okay, so let's do a quick overview of quantum computing. So let's say I have a qubit, and I'll call it psi. So I can represent it like this, where the norm of a squared is the probability that the qubit is in state 0, and the norm of b squared is the probability that it's in state 1. Now let's say we have two qubits, psi1 and psi2. So I can either show them like this separately, or I can take a tensor product of the two things, and I'll end up with something that looks like that, where each of these coefficients represents, the norm squared of each of these coefficients represents the probability of the two qubits being in that given state. And this, all these coefficients, when you put them in a vector, that's called the state vector of this tensor product, and that state vector is what I evolved in my QCA. Okay, so let's say I start with 3 qubits, for example. So this is what my initial state would look like, and I have 8 coefficients, as you can see. Okay, so now I want to evolve this state. So I'll take an operator U, which is any unitary arity 2 unitary operator, and I'll put in my first 2 qubits in it, and I'll get 2 new qubits out of that, and that'll be my intermediate psi 0, 1 prime state. Then I'll take the next 2 qubits, and so Q2, Q3, and then Q1 and Q3, and then I'll add all of them together to get my new final psi1 state. Okay, so I can write this big U as this sum of all these little u's, and let's say if I have more than 3 qubits, I can show it like this. And if I have more than one operator, let's say I want to have m different operators, so I want to apply u and then another u that are all different, then I can write big U like this. So for an arbitrary state, p, I just need to apply big U p times onto psi naught to get my psi p. There's a note I'd like to make about enumeration. So in Stephen Wolfram's classical cellular automata, he has like a finite number of rules that he can apply. But in my QCAs, I'm just all my operators are just unitary matrices. So if you have a way of enumerating unitary matrices, please let me know, because yeah, I don't know how to enumerate those yet. Okay, so here's an example. This function quantum tensor automaton is in the function repository, and if I start with 4 qubits, so I'll have 2 to the 4 or 16 things in my state vector, and I'll just evolve it for 1 time step, and I'll end up with this. But I don't really know what to make of this. So Stephen Wolfram had like these black and white things in his CAs, but how do I show a complex number? So I had to come up with some visualization scheme for that, and this is what I came up with. Oh, it's not the best, but if you have any better ideas, please let me know. So the red is a 1, the pure green is like a -1, black is 0, and so on. And any complex number is just a composition of these colors. So if I apply, now we can see this better, I guess, maybe. If I apply this random unitary operator onto this initial state for 10 steps, this is what it's going to look like. Let's look at some more examples. This is another random unitary operator, and another one. As you can see, there's like patterns, or like it looks like, oh, it's repeating itself, but then sometimes it's not repeating itself. It's got like little fluctuations. So I wanted to actually get numbers on these things. So I did what almost every physicist does. With a state vector, I took the norm squared, and I plotted those over time. So I plotted the probabilities of being in a given state over time. And here's what I got. So as you can see, when I start off with any initial these are all 6 random unitary operators, and I start off with an initial condition, and they all reach an equilibrium state, which is pretty interesting, I think. Yeah, when I showed this to physicists, they were like, yeah, the system, yeah, you're applying a Hamiltonian, so the system reaches equilibrium. But when I thought about what I actually did, which is just multiply a matrix with a vector a bunch of times, it didn't really make sense to me. It was really weird and interesting. So this was a cool thing that I found. So what next? Well, I could change the initial conditions. I could change the operators, see how that affects it. I could try connecting it to the real world. Pretty much do everything that Stephen Wolfram did in NKS I could do with this model. So when I showed this to my mentor, Jonathan, he came up with a conjecture, or a way to connect it to the real world, and this was it. So here is something from Leonard Suskind's work. Alice falls into a black hole. Bob sees Alice get redshifted. He attempts to reconstruct her from the redshifted state. The computational complexity required for Bob to reconstruct Alice is related to the time taken for Alice to fall into the black hole in Bob's reference frame. So the way that this connects to my QCAs is that, for example, I start off with an initial state, and that's my Alice. She falls into the black hole and reaches this equilibrium state, which is her redshifted state. So the amount of computational complexity required to start with that equilibrium state and go back to initially Alice would be that computational complexity. So the time taken to reach that equilibrium state should be somehow related to the computational complexity required to go back to Alice, starting with the thermalized state. And so we tried to prove this conjecture over the following months, over the summer school, after the summer school. Okay, so first off, equilibrium time. How do you measure the equilibrium time of a given QCA? Well, I just did it in the most obvious way that you could. I looked at the norm squared, and I said, okay, when do these stop changing? Or when is the difference smaller than a given threshold? And the number of time steps that it took to reach that, for that difference to reach that threshold, that was the equilibrium time. I think my threshold was around 10 to the negative 12, I believe. Yeah, and I did this for 100 different initial conditions and 50 different operators. And here's what I got. So the blue is the mean, and the yellow is the standard deviation. This graph right here is averaged over initial conditions, and this one is averaged over operators. So as you can see, the equilibrium time greatly depends on the operator, but doesn't really care about the initial conditions, which is pretty interesting. Now you may look at this graph and wonder what that giant peak right there is doing. And I wondered the same thing. So I looked at it, and this is what it looks like. So you can also see things like resonance in these QCAs, where if I evolve this operator for like 800 steps, it'll reach equilibrium, whereas the ones previously that I showed only took like about 50. So this resonance feature is really interesting, and we're still not sure why certain matrices show this type of resonance. So if you have any ideas, let me know. Another thing I looked at for the equilibrium times is the rate of convergence. So how fast does a QC reach its equilibrium? And we found out that it was exponential. Yeah, and this is a plot of the change in the norms over time. Okay, so now on to the complexity. So the computational complexity, this was a little bit trickier, but yeah, so given this equilibrium state, Bob needs to multiply this equilibrium state with R to get the initial Alice state. And the condition that we imposed on this R was that any R that is Hermitian. And the reason we did this is because given physically what the scrambling complexity is how convoluted does the measurement apparatus need to be in order to measure the equilibrium state as the initial state. But another reason we had to impose this condition is we couldn't, if we imposed that R was unitary, it took way too long for phi instance to find an R that was unitary, so we said, okay, a Hermitian R also kind of makes sense. And then after you find that R, you can add over the norm squared of the eigenvalues, and that'll give you your complexity. And then I did the same thing. I did it for 100 initial conditions, 50 operators, and this is what I got. On the right, again, averaged over initial conditions. On the left, operators, and you can see that similar behavior that the operator, again, largely determines everything. So that was like a big takeaway from this. Like the operator largely determines the equilibrium state, the equilibrium time, and the computational complexity, which was interesting. And now came the time to relate the two, and we got a nonlinear relationship with an R-squared value of 0.934, which was pretty good. But again, this can also be greatly improved by, again, maybe imposing that R is unitary, finding different ways to calculate complexity and so on. So yeah, those are also the next steps. So maybe collect more data to improve that R-squared value, improve the complexity analysis. We can also validate more conjectures. All of this is also written at the end of our paper, if you are interested. And that's it. I'd like to thank you for listening to my talk. And I'd also like to say that I am looking for a job from January to April. So if you have anything available, please contact me. Thank you. That is all.